So yesterday we have done the stochastic heat engine in the context of like single polar particle in an harmonic trap battery quasi-static, right? So today what we will do, same setup but non-quasi-static, which essentially means the time-dependent drive is the rate change of time-dependent drive, lambda dot, this is d lambda dt, is not 0, and there we need a particular form of lambda, right? Some particular form we need to calculate for a particular drive, and what will decide the form? So lambda t will be decided by optimization of delta S total. So we'll optimize the dissipation. This is the dissipation, and we will optimize it, and that will fix your lambda. The least dissipation protocols. You can there are many other ways to optimize many other quantities. For example, you can directly optimize efficiency, you can directly optimize work. Here we choose to optimize dissipation. Okay, but they are related to each other. So this is today's thing, and of course we will do the simplest possible system that we are considering. Otherwise, doing analytical progress is difficult, but you can computer you can do. Then there is you have to consider the optimal various optimization process in the simulation. So here it is very simple. At least we can proceed analytically completely. So that's why I choose this example. Okay. So the equation so we will do the algebra for overdamped. Yesterday we did underdamped, but there was no dynamics. But here we follow the overdamped. Underdamped will go exactly same way. Just it is algebraically little. Say I have to add one more term regarding the kinetic energy. So that's why I am just dropping that one. We do it overdamped. You will see that the underdamped will follow. Okay. As far as we consider the harmonic potential. So gamma x dot minus lambda t x plus. So this is the by now I guess you know everything of this equation, which is from day one. Okay. So this is standard. So delta 0. And we know the average, so W. So these are. So I'm not taking this symbol anymore. It's everything averaged over. Okay, so is like half lambda dot omega dt, where omega is x square average, x bar square, where this one is 0, x square. So first step is, so for optimization, we need, like we did as far as thinking about the students. So where do you face so far the optimization problem in up to say MSc? You have faced definitely somewhere the optimization problem. Do you remember? Huh? Lagrange multiplier. I mean classical mechanics, right? So the classical mechanics starts with some kind of optimization principle. You get the Euler-Lagrange from optimization, right? So there, what we do, we basically, this delta is a particular meaning for optimization, right? This delta, we take this Lagrangian, and then we have 0. And this gives you Euler-Lagrange, right? Now, here also, it goes with a similar track. But it's not Lagrangian, but this. This has to be, so we are trying to find some lambda which will optimize delta S total, right? So from here, we have to write the, in terms of delta S total, but it should be a functional of lambda. So everyone is clear about what is functional is, right? Okay. So this should be a functional of lambda. That means that we will, so functional is what? Functional is like we take a function and then put that into that functional, it will give you a number. So there it is a difference. It is not a function of a function, right? So it will take a function and it will give you a number. So it should involve an integral. You have to integrate over, right? That's what the functional is. So we need to convert this thing as a functional of lambda. And then we will apply C. So same thing, instead of L, we will have W, and we will get the Euler-Lagrange equation for W.
So won't we maximize that action LD?
Yeah, so that is, I'm just, okay, I'm quite sorry. So this is like S, so here is the integral. This you have to, and this will give you, okay. So this is exactly the path I will follow. Very, same. Okay, we will derive an Euler-Lagrange equation for this.
Just kindly remind me what is the connection between W and delta S?
It will come.
But you have to optimize delta S, right? Not
it will come. I'll so to our first step is to do a bypass here. So first, this is from some initial time to some final time, say Pi to Tf, lambda dot dt minus omega dot so this I did just the bypass. So the first term is half lambda omega Tf then minus half here. A simple step of bypass.
So the index dt prime will be there?
No, I just put this. This means omega. Okay, this delta x. So from here, x is x0 e to the power lambda minus I. So here lambda is a time dependent thing, so I cannot, means there is a, I have to put the integral here. Then I have 0 this is multiplication. Am I correct? Is this, or am I missing some term or some coefficients? If I miss something, something will come up. Let's see.
So, let me
Yes.
understand, but you started with W as if you wanted to write, what is W? W is a work.
Which, that one? Capital W?
Upper board, capital W, right?
That is what? Average one.
Average work, I see you left that.
I just,
So you are starting from the definition of that work which is given in this bracket, or you have done some
which
operation.
bracket? So I just take this term as a like bypass. After so I did one step there, and then I go back to the equation and derive
I mean,
square.
what is the difference between the first definition of W? W is equal to half lambda dot omega t, and then the second.
This one?
So you W equal or W?
No. I from this step to this step is just a bypass. Integration of bypass, nothing else. This is the first step to step. This step clear? Like, this is the definition. From there to there is just integration by parts.
Oh,
Okay?
yeah.
Is there some? Wait, so gamma by 2, so okay, there is a right, you were right, so 2 by gamma will be there. Yes, because, yeah. Yes. Then 2 by gamma. Then
But you are solving for x or you are solving for omega?
this one is solved for omega.
So the one written there is for x.
This is for x. I will. So I haven't derived, I haven't, so I just take this.
Square is
Right.
equal.
That's what I was.
Yeah, no, I did not see, sorry.
No, that's why there is an arrow. Arrows are important.
Should I take?
Yes. This stochastic thermodynamics arrow is everything.
So Arnav, that capital W, that's what, right?
Sorry, again?
That capital W, which is
This is average work.
why is it being work done in some time? Why is it lambda not omega?
Okay, so the definition of work.
It's half kx square.
So this is a potential u of x
Yeah.
lambda. Here it is harmonic.
Yeah.
Then W is del u del t.
Yeah.
Say t final.
Okay, fine.
Then you have this lambda and delta t, so lambda dot. U is here, say half lambda t.
Yeah, but why is it x square average there?
Oh no, I took the average. So here it is stochastic set. I took the average. I don't write the symbol. I just, so this is average one. Is it clear now?
From the dynamic equation minus lambda t x square. Second equation.
This one, yes.
When you're taking average, the second term, I'm confused with that. X
Huh.
square.
Then average is this. So this is omega.
You're not averaging over lambda.
Lambda is a definite deterministic function. It's not a random function. So x is what is random. So then eta x average is, this is x naught is independent, this is initial condition, so independent of x, and here I will get 1 by gamma to the power so eta prime, so this will be like 2 gamma kbt delta t minus t prime into the power 1 by gamma t prime. So this will be like to the power, so one, but this gamma cancels out 2 kVt, and then you have half like this. Is it correct? This is just simply kVt. This is delta t minus t prime. Then I have to do this integral. This is t up to t, so at half it will come as half. And then this gamma cancelled out. This is simply kVt. So for any lambda, any time dependence, this kVt. That means we get t omega. So similar derivation we did in the first class, that for this delta S total average problem, that was for constant k, but this result is for any lambda. Okay. So then this is, say 1 by gamma is mu, so 2 lambda plus 2.
Also, I didn't get this half part. So I didn't get this half. What is half?
So this delta t minus t prime up, so if we, when it is minus infinity to plus infinity, not any delta function, it is 1, but it is up to t, right? This is finite time. That's why it is half. So this is okay, this we have taken that time also, like the first this one lecture. So now this is the dynamical equation for my x square average omega. This I need. So this is omega dot, right? So we have
this is eta is the noise of bath,
it is a noise of bath, yes.
and x, I mean eta into x is not depending on any effect on of noise lambda. I mean
It depends on cavity only,
it's
the temperature.
strange, like no effect of lambda, right? I mean, how can one easily understand? I mean, this is mathematics, but this is
Eta x average. Why you mean why it depends on temperature only?
yeah. I mean, not no effect of detail of lambda is coming into it. I mean, the change in lambda effect of lambda.
That maybe because I haven't thought of, but maybe because x average is also independent of lambda. X average is also 0, right? From this solution, if I take the average here, if x0 average is 0, the initial condition, this one will also not contribute. Just symmetric writing. That's why maybe.
I mean, one simple analogy is suppose you have a particle in a potential half kx square, then half mv square does not depend on the k, right? It's just kv. It's a, it will be along that line.
So here, so now I go back in this expression. So we know this d omega dt, what is that? So W this is a boundary term, so it's not entering as a functional form. This one omega dot is there. I will replace this lambda. So what is lambda here? Omega dot mu kbt minus omega dot by 2 mu lambda. This is, oh no, sorry, this is my lambda. From this equation. Correct? So I just change like 2 mu kbt minus omega dot, then 2 mu omega is my lambda, which I am going to do. step. I derive a equation for dynamical equation for omega. From there, I replace the lambda in the definition of average work. Are you with me, the students? Is it clear? Let's simplify a bit.
These are all averaging, right? Averages like omega.
These are all average. I am not talking about anything now so far, like trajectory dependent. Average over all possible trajectories. Because I average over noise.
Except for lambda t.
Lambda t is a deterministic function, no point in averaging. Okay, all the random quantities are averaged.
Why did you put the lambda expression in the first?
This will immediately clear. Next step. So this is going to be the first law, as Mandava asked, why we are minimizing delta S total, or where is the delta S total rather? It will come.
No, I'm looking at you see,
Just give me 1 second. 1 second. Yes.
see, we have got eta x average is kbt, right?
Yes.
And we have eta correlation,
Delta.
right? I mean eta t prime delta, and that is at 2 kbt gamma, right?
2 gamma kbt multiplied by delta.
Delta. And here it is also I mean same time, right? Eta in the equal time, right?
Huh. That's
So it
yeah.
means this x is, I can write x as like it's highly correlated with eta, right?
X.
Yeah.
Yeah, X is a linear function of eta.
X is linear function of eta.
Yes.
Right?
Yes. Yes. That's why X average becomes 0. Because eta average becomes 0. Yes.
So, I mean, all this thing is coming over here. Lambda becomes a specific function of time, right? Independence of lambda.
So lambda becomes a function of omega. So of course, means lambda is in your hand. You have to control. Means in experiments you are fixing what my lambda is. You can fix any lambda. In that sense, it is independent of your lambda is your input to the system. Correct? Lambda you fix. But now I ask us a little bit different question, that I know that I can fix any lambda, but I don't want that. I want to fix one particular lambda which will optimize my omega. That's why this dependence is there. Okay? Yeah, some.
Meaning at every instant you want to get KBT, half K. I mean, sorry.
This is anyway, any lambda I have, for any lambda it is there. I can't change that as long as.
Omega is K dependent.
Omega is X square average, yeah.
So then lambda
This,
is-
yeah, exactly.
Okay.
This relation, of course, It is true everywhere. But here the interpretation is little different. Here I am not going to fix whatever lambda I want. I choose. I have to fix one depending. I have some requirement. I have to extremize or minimize this delta S total. There, that condition fixes my lambda, and that is why lambda is tacitly dependent on this.
So you solve this equation for a given
In terms of
lambda
lambda,
and find
yes.
out small
Yes.
lambda.
Yes.
And then you put in there.
Then I will put there again and get back to lambda. This is the optimization strategy. Okay, now where is my first law? Where is delta S total? Okay, one step further. Just a second. Yes, oh,
So I
there's
think the middle term is omega dot square by omega.
middle term, this one
Yes, sir.
is what?
Yes, so omega dot is square by omega
This is there.
t and this will be single omega dot. Yes, sir.
No. This is omega dot.
Yes, sir.
So omega dot
That is on
square.
the right with-
What? Okay. Yes.
Omega dot is square.
So the first term is omega 1.
That will
Omega
omega
dot by
dot square
omega.
by omega t.
Oh, this is fine. This is omega dot by omega,
We
right?
have interchanged the terms.
There is a minus sign. So I think
Okay.
the sign there.
No.
This is minus.
Sir, but
This is
KVT
minus
term is
plus.
also.
Yeah.
Like this.
KVT.
No, sir, but KVT term is multiplied with omega dot by.
KVT will. So the KVT will be here. The KVT will also be there.
There.
Yeah.
Okay. Let me check. Yes. Correct.
Many people correcting you.
Very good. That's I like actually.
I know that's confusing.
This is KBT by 2 and this is okay, right? KBT by 2 and this is
Same pair of eyes.
But happily they are something the same.
now correct? Very good. So it shows that they are with me. So now this is what? This is my delta E, if you like. This internal energy difference. This is what? This is my delta S system. Correct?
All average.
All average. All average. Now, as a first law, what should I have? This W is,
I did not understand the.
wait, this. Why it is delta S system, right? Okay, this one. Okay, let me.
You finish it and then.
Yeah, so del W is delta E plus delta Q. This is so this is the system bath thing, right? Exactly. So if this is my whole bath thing, and here it is my, I will go into it, but this is my system entropy, then this has to be minus total entropy, because the whole thing is the bath entropy. This is system entropy. So this has to be S total average. I will use this. Why this is system entropy? So this is Gaussian. So P of xt is in general, we know that 2 pi. So this is my omega, okay? So is ln, this is same omega.
Why do you say P of S comma T is this? Because the lambda is.
This is Gaussian. I mean, when I wrote this xt as a function, it's a linear function of eta, and eta is Gaussian.
Okay, that is fine, but you have lambda also.
It doesn't matter.
It's a time
See,
dependent lambda.
yeah, but x of t, it is an integral. There is a linear function of some random variable. So it doesn't matter whether it is lambda, how it depends on time or not. But if you have some random variable x, say, which is a function y of some other random variable eta, which is a linear function, say, okay, then whatever statistics is followed by eta will be followed by x.
No, my only point is that x square need not be, it can be time dependent also.
It is there. So it is t.
No, x that
X square
average.
Yeah, right.
It can be time dependent. It will be time dependent actually. But the form is Gaussian.
Comes to lambda.
Hmm?
The time dependence
The time dependence comes to lambda, but the form is Gaussian. It has to be. It is time dependent. So this is x square 2 omega.
Only that the mean is not affected by lambda. That
Yes,
is
because of this,
Yes.
it is kx, the lambda itself. So now, if I want to get the system entropy, average system entropy there, I'm actually calculating the Shannon. With a minus sign. Then first term will give me what? One. This is the normalized, right? And the second term will give me what? Half. Because this will cancel x square average. So now you see this is my delta S total. Sorry, delta S system.
Sir, isn't it 1 by root 2 by x square average? Like, isn't it 1 by root 2 by x square average?
The x square average is
No.
omega.
No, 1 by root 2 pi instead of 2 pi.
Or root 2 pi, na?
1 by root 2 pi.
Maybe
in
yes.
the 5 would inside.
So this goes in inside.
Yes.
This will not matter because it will cancel out anyway. But of course, one has to be correct. So now if I calculate this, means two different states, between two different states, I will get that ln. So this will be proportional. This is ln omega. Correct?
Correct sign.
We will sign this. Okay. So this is from Ti to Tf. So then I will be getting this. We have to have the difference of S total, S system.
Why is it that part is total minus its system? I mean that.
So this is from first law that we have internal energy in the right hand side. The rest what we have coming from Bath.
Yeah.
Right? This is first law, independent of that.
Oh, so this whole thing is del Q.
Yes. So whole thing should be del Q, and now I get what is my system entropy. Then it has to be minus of total entropy.
And that is the, yeah,
That
the
is
system.
yes.
Yeah.
Why it is system entropy? That is there.
No, but that should be divided by T. I mean,
T is there. I'm just talking about like T's anyway.
capital T, I mean temperature.
Yeah, that is there. So my point is, see, these first two terms is the boundary terms. So they will not enter This is an integral term that enters. So I have to, that means this is my total entropy. That means average total entropy. That means I am actually extremizing the average total entropy, which is the dissipation. So I am extremizing the dissipation.
So up to now you have not applied any, optimization or.
No. I will do. So this is, I am talking about the strategy, what I am following. Is it clean for everyone?
Sir, can you repeat why you are calling delta as total as dissipation?
Okay, delta is why it is dissipation. So you remember in one class so delta is total shortage of board. So delta is total. If you remember, so this was something d p forward, p backward. Do you remember this? This is the so okay. So when a system, say we drive the system, okay, and we can also, so the system can go forward, and then we can make the system to go back. So there is a backward trajectory. That's all about the stochastic thermodynamics, initial 2-3 lectures from Abhishek. So these two paths, forward and reverse, why they are different? That difference shows up in the total entropy. This is a definition we follow, right? So the difference between forward and reverse path, why there is difference? Because there is dissipation. And that measured by this. If these two are equal, then this is 0. So delta S total entropy is 0. That means no dissipation. This is a reversible case or quasi-static case. When there is a difference, then delta S total is non-zero. That means it is giving a measure of dissipation. Clear?
Dissipation of what?
The system, the particle.
Energy.
Energy. Okay. Fine. So we have this. So now we have to go real optimization process. Up to this, is it clear? Everything? Debater is not happy. Some problem there must be. Sign problem is there.
There is a sign. There is a sign.
Which one? Maybe, okay, well, maybe I do mistake always. Is there?
I thought that I need the heat. I know that. Since I am in the radius.
What?
Nothing.
So here we are not saying whether it's the work done by the system or on the system. We are just
Not yet. So that's why.
making generic.
Yes. But it will come actually. I have to do that. So this is my just to rewrite the function. W is half final So delta, this is now the classical mechanics, will give me dt, it is the Euler-Lagrange of W. So this is, I have to do the derivatives now. So only omega dot coming here. So this will come del W del omega dot is, so now as you know, this omega dot and omega are independent variables. So as Lagrangians. So this 2 omega dot 1 omega minus omega dot square plus. Is the first step correct? So this is now 2 double dot.
Why to go in second derivative, one can use omega dot by omega as a one variable.
Tell me.
I'm saying omega dot by omega is used as a one variable, we can solve it.
As a one variable?
Omega dot by omega is it?
No, it is like Lagrangian. So you have this
Like x and x dot are independent.
like P.
No, that's fine. I'm not saying final differential equation what you are writing. Solution, I am saying omega dot by omega can be considered as a one variable and solve it directly.
No, solve it directly what?
This differential equation.
This differential equation.
Final differential equation.
Final
Yeah.
here.
So before this, this
Again, one integration you have to begin.
Again, you have to do the one.
well,
But anyway, yeah, this can be done in many ways. But so this is my equation of motion. Correct? So this is my Lagrangian, Euler-Lagrange equation of motion.
So it is that EF parallel PD, what is that PD? What do you mean? EF parallel, the delta is.
Oh, this one that one student asked that why this is notation, nothing else. This is the Leibler-Kullback divergence notation that someone asked that what is your dissipation and all, why delta is total is
P is what?
this P is probably also backward forward.
Oh, okay.
If we just did all the simplification just to get the idea that we are talking about dissipation, because by not doing all of this, we will get the same answer. Just doing the just optimizing the first the term.
No, see, we have, okay, this can be done in many ways, multiple ways maybe. This is one way that you have to write this W what as a functional of omega, then you have to take the functional derivative 0, first derivative, then, so this is one way, but Maybe there is some other like parallel ways or so.
No, suppose given the Langevin equation, given the lambda t, I know per unit time what is the energy loss.
You know lambda t, but you know the functional dependence on
I
time.
mean the power loss into that is lambda x dot.
Yes, but you know means like you know the function of lambda t?
No, let's say
For any
what
lambda.
I'm saying is the total W, I can just write down
In terms of lambda.
integration from initial to final,
Yes.
lambda x dot integrated over.
Yes. There are. So this is one way actually I am following, but
in that case, we have to calculate x dot.
yes.
But
Yes.
that,
X dot is v.
X dot is 0, right? I mean, we are assuming
X dot-
instant x dot is.
No, in that case, what I think that you
You
have
came
to.
from x square average root, right?
Mhm.
Which is non-zero,
Mhm.
and give you some
Mhm.
finite answer. But if I do x dot average,
Actually,
wrong.
the equation that to arrive there, because the function that we are talking about, I think that will be extremized with lambda, not with.
No, but not
Then-
get to the expression for
Okay.
W. After that, I will do this anyway.
So there is a
Energy
lambda.
loss is lambda x dot square. I mean, look at the Langevin equation.
There is a lambda t term. So
Yeah, lambda into, I mean, friction into x dot. That is the loss, right? Energy loss.
Gamma x dot.
Gamma x dot.
gamma is lambda t.
Gamma x dot
Gamma
is
x dot is the original equation, and then
gamma x dot is lambda x plus eta.
Yeah, we did the same thing. Why I'm asking is
Lambda is time dependent.
Lambda is time dependent. So gamma x dot is minus lambda of tx plus eta. Yeah. No, it has a point, but this thing I
will
thought
talk
of
about
it.
it. Let's talk about it.
Okay, now we have to okay. Ln omega, that bound. So that is a boundary term.
There's something wrong there.
Huh.
why you put it to
Yes.
If you put what's the other type of noise, then you couldn't.
Other type of noise, then the solution that I wrote in the beginning and saying that is the Gaussian variable is not there anymore. So in that case, I think this term will be something also. Well, first law is always valid, right? So that means that this term will have some different forms in case of this thing. That is it.
Coefficients are not
No, this is not coming up, but it is the equation of motion now in omega. So if you now can solve it actually this. So omega, this equation, though it is nonlinear, but it is easily solvable, fortunately. Okay. So how you solve it? Let me write the first the solution. So there will be two constant. So this is the solution. So yes.
So linear and last time also wanted consider this total.
This is the logic is like these two together has to be your path entropies, right? When I mean heat from the path. This you know it is system. So this has to be total.
So that's the different.
Of course. They do it like I might miss it somewhere. No, this is your where is my so this by or so I have to multiply or divide by the temperature to get this thing. So there is a temperature, right? So but it will be a constant outside. So it will not enter into the delta is total by T. So to make it heat, we have to multiply, I guess. By the way, this is so it will now. So is it obvious that this equation will have this solution?
Actually, coming as that way, if you take omega dot by omega as the variable, it just comes in two lines.
Omega.
Omega dot by omega.
Ah, okay. It will come in two lines. Yes, exactly. So this one, then this seems. Now we have to put the boundary conditions to get these constants, C and C. Okay. So there is a cycle. So it is cycle. So it starts from, say, at t is equal to 0, the starting point. Omega 0 is, we know, say, is omega A. We need some boundary condition to solve fully. Right? And this has to be, as it is periodic, this is cycle time, has to be same as omega A. Right? Then, so omega.
Why is it periodic?
Cycle. So finally, so far I haven't talked about anything regarding that we are doing engine. No engine property is there so far up to this solution. So now I have to put properties of engine, that is cyclic and.
So your TF is tau.
Yeah?
TF is tau now.
Yes.
Okay.
Yes. And TI. So tau is the cycle time.
Four such piecewise relations.
Right, exactly. So omega A to say, so when I start my cycle, the first isothermal, hot isothermal, that is, we start with omega A, okay? Then I go through this isothermal, comes at that, then my, this one, with comes omega B, then I have to get back omega A again after the. So these are the boundary conditions. Okay? So I'm going about time. Is over?
No, we have half an hour.
Very good. Half an hour.
So optimizing, do we know whether it's maximized or minimized?
Yes, but I mean, I will not do it here, but if you take the double.
Yeah, but that is what? Is it minimized?
Minimized. Delta is total.
I mean, I don't think that's what that solution was working. It seems, I mean, maybe trivial, but
What?
I mean, there are many other solutions also for this, right? For example, if I take trivial solution,
once
omega
you-
equal to constant.
No. Other solution. Once I fix the C and CV with the engine boundary conditions, then there will be unique solution. So far there can be many solutions, right? Because these are all general solutions.
No, what about the functional form?
Oh, functional form.
Functional form, yeah. Functional form is not that form actually.
No, I guess this I means I can do it
Okay.
fully, but
I don't understand. Why are we emphasizing on this form still?
no, I can. This is the form, I guess. There is no other form. I can, yeah, this is the form. So for convincing you, I can do it, just like there. Yeah, you just have a look in there. This is just notation, that is a constant. So these are the boundary conditions. There is no meaning like A and B. So omega A is the width from where we start, and omega B is the width where this first hot isothermal path ends. So there's engine right now. Now I'm putting the properties of engine. So this, then again this. And we have to go back to omega A for cyclicity. Okay, then let's put the boundary condition first. So this is my omega is at t is equal to 0 is my omega. That t is equal to 0 signifies the first point of the cycle starts, the first point of the first hot isothermal. Omega A is CA. So now it is for isothermal expansion. Say this time is tau hi. This is my notation. Hot isothermal. This is the time scale there. So it means omega B is omega A from here 1 plus CB tau hi square, which will give you CB as omega B by omega A under root minus 1 by tau hi. This is hot isothermal. This is the isothermal expansion.
So this is the first step you are doing.
First step.
This calculation which showed that omega, which is x square average, should behave like that in order to extend W.
Yes.
So that means the trap should expand linearly. So that omega is x square average.
Yes. But actually, x square average is this. So that means it should have some, not linear, it is square there.
No, but it's x square average.
X square average. So that
the square root of x square average should linearly expand.
so linear, yeah. But there is jumps. I need it. So it is not, there is expansion, there is compression, and in between there is jumps. It will come. So even if in the optimized protocol we have those jumps that we have taken earlier without knowing that we are actually optimizing. So the example that we took it that time in a sense, simple thing, that we have this expansion and then there is jump, there is compression, then again jump.
But your aim was to find out how should lambda
Yeah. So here it is omega. No. What I'm saying is, this one is, I will reach there. That what is the lambda finally? Optimized lambda. Okay. What I'm saying is, yesterday we took these jumps also, the adiabatic jumps, saying that okay, instantaneous jumps, so no heat should be inside or going outside. So I take this instantaneous. But here, after doing optimization, I get those jumps. That means the jump length will be different. That is true. But those jumps are required even to optimize the system, to optimize the dissipation. Okay. Yesterday we took it unknowingly. Now we took it knowingly. That this is the optimized thing.
how do you find lambda from there?
Will come. So we had a relation between lambda and omega, right? We discussed just few pages back. So
It's a function of the relation where you get omega dot and omega dot.
Oh,
yes.
okay.
So there I will put the omega and omega dot and get the lambda back. So my omega, which is omega at t, h, I, this part I see. So we know now CA and CB. So this is omega A 1 plus so this is my optimized omega along the hot isothermal path. That is the first isothermal expansion. Okay.
So you say this expansion because CB is positive, using that. And why is it an expansion? The CB
No, why it is an expansion? Because I chose that this particular boundary condition I will use at my, so this is this omega A is the, so there is a cycle here, say,
now, yes.
here this is my omega A and from there it runs. Therefore I fix this will be my, but
tau I thought was the whole cycle time.
no, this is tau HI, tau hot isothermal, this is not full tau.
Okay.
So B is the endpoint of the isothermal.
These are
B.
Right. B is the endpoint. B is the endpoint of the isothermal. Omega B.
So omega B has to be greater than omega A.
Yes.
So you have to assume CB is positive.
Yes. Yes.
That's the expansion.
It has to be greater than omega A. That is why there is no like. How is process means which process? That's what I have to. This is the input to my theory. So far, but up to this, and even solving this in generic terms, like with CA and CB, arbitrary CA and CB, up to this there is no engine. So there is no engine. I just have some lambda. I can do it.
I think he's asking if this can be an isobaric expansion as well.
Other kind of.
Oh, other kind of.
Or adiabatic or whatever.
No. This is again so I'm following the same protocol as I explained yesterday. The same engine. Then what about the optimization? So I'm not changing my system. You can do this isobaric and all, but where this will change?
Single Langevin equation, single part, how will you get pressure here?
How will get pressure? But we get volume, so
I think
there must be some measure.
in this information there is nothing about isothermal process. Only thing is that omega B is greater
No,
than
because
omega.
this
No,
calculation
isothermal is like we have kept the
temperature.
temperature of the bath same.
Fixed.
So that is why the isothermal comes. But the isobaric, like constant pressure, there is a volume. So,
What is the volume?
no, I mean volume is like volume analogous, x square average is there. So I am thinking that whether by similar way one
This
can.
calculation constraints seem to do it at fixed temperature.
Yeah. Huh? What?
This calculation constraints seem to do it at fixed temperature.
Yes. No,
All these
what he is saying that whether I can have similar process but in some other kind of engine where we have isobaric or
then the equation will change. Right?
the equation will change. I'm just trying to guess that where the changes will happen. Not very clear to me.
Then that contains the temperature.
Yes.
Contains the temperature.
Huh.
There we can we use ideal gas? The T is changed to P.
But there is no information of pressure in either equation itself. So we can't solve for
That temperature.
Maybe
This one you wrote, I mean, whatever we have done this at one point, right? Up to now, W, you wrote change in W and all.
I wrote this now, the time dependence of W. There is time here.
This is omega.
I
I mean,
W I will come. So far,
W was only written, what assumption that W was written?
just from the definition, no assumption.
So, up to now there is, I mean, so you were calculating W as, you were having a Lagrange.
So I am not have, so far I haven't calculated W, I just calculated omega. So far.
Definition of W
Will come. So what I will do here from there, I will first calculate what is my optimized lambda. So there is a relation between lambda and omega.
Now you have optimized this W, right?
Yes.
This W has a definition, right? Starting.
Yeah, half lambda W dot. Half lambda omega dot.
Right. There is no reference to any process over there.
No. I will, so while I put here this thing.
But W will be defined for the path, right?
No, but this is average W I'm talking about.
No, whatever, but it will define.
It will
W can be defined for single path also, right?
No, I'm not.
I was thinking, like, if it's an isobaric, it can't be at the same temperature, right? So your equations will not.
Yeah. So that is so there has to be something else we needed from the beginning onwards. Okay, let me. So what about then? So this solution now I am trying to find for cold isothermal omega. So the same solution I took, now I want to calculate for the compression path, right? So this is T minus hot isotherm, tau hot isotherm up to which the hot isotherm is. Same, the boundary condition I will put here. Similarly, so we'll get omega cold isotherm. No, but this is T minus. So it has to complete the hot isotherm, then the cold isotherm should start, right? So T is greater or equal to hot isotherm. We'll come to the cold isotherm path this one time in a moment. So omega B is when T is equal to tau Hi, so it is 0, so Ca prime. So when T is equal to tau Hi and omega A is omega B 1 minus Cp prime. This is by tau minus, this is total cycle time. This will give you.
So is the switch from the hot to the cold isotherm instantaneous?
Instantaneous.
That's why you are setting the time.
Exactly.
Initial time will be
Exactly. So this thing is there that if I switch instantaneously, because this is the requirement of adaptability. If I switch instantaneously, no heat should enter or come out. This is not the only, of course, the thing, but this is one way to implement adaptive conditions.
So no, tau H1 plus tau C1 will be your entire cycle.
Right. Because adaptive jumps are instantaneous. And this instantaneity I need for adaptive. Right? This is one way to implement adaptive.
But the work
CV prime is
The work will still be done during the adiabatic. Work will still be done during the adiabatic.
yes. That is okay. So that we will deal with as we dealt earlier yesterday. So the jumps are required for implementing.
Doesn't that make the power infinity during that?
That's it.
No, because it is like instantaneous thing. No, it will not be infinite. So we'll calculate the power here because P is
W by P.
Y power is not.
W at the cost of internal and system.
Yeah, that you remember we calculate in the adiabatic part. The work is the internal energy difference.
Yeah,
But there is
By definition, it is dW by d. I mean delta W by time taken. The time taken is very
instantaneous. That is why you are saying that.
So it's quite high. But the thing is, we say this is instantaneous.
No, but see, no. The point is the power of a cycle is like P tau Hi tau Ci plus this. So I still have this tau Ci plus tau Hi, right?
Finite.
So in instantaneous time, say it is very small or zero even. When you calculate the total power of a cycle, that means that W, the work done in total cycle, by this tau Hi plus tau Ci will be there, plus something, maybe zero.
No, I think it will get cancelled out due to the other area.
No, cancellation is not there, I guess.
cancel.
Work can't.
But the point is like this, it is not the only time that goes into this adiabatic frame, it is also the isothermal times. So you neglect that time in terms of those isothermal times. So this is omega A. So these are the two constants. So I have cold isothermal, so this is my optimized width along the cold isothermal, and that was my optimized width along the hot isothermal. Between there is jump. So this optimization process actually gives you the extent of the jumps. Okay. So now we have this lambda T, that's I just report actually from earlier this thing. Was there a gamma there or anyway mu lambda kV, oh okay, kV is there. So here it is now very straightforward. I have these two expressions. We can have lambda optimized. Just putting these two.
meaning two different lambdas.
Two different lambdas.
In the
Lambda in the isothermal, lambda in
expansion of
the expansion, in the compression, and they have jumps. You have to match the jumps.
What I didn't understand is that for isothermal, hot and cold isothermal,
Yes.
why do you still have omega A and omega B? Those are the starting.
They are the boundary conditions. That you have to still provide. Because we need those boundary conditions to get the unique solution.
But those, in each of them are not identical, right? They are separate.
Yeah, because this omega A is the initial point of the the expansion, initial width, then it decreases, right? And reaches up to omega B. There has to be different.
Yeah, no, that is fine. But for the next cycle, the cold
Next,
cycle,
not next cycle, same cycle.
no, the cold.
But see, this has to be at the end of the day. This omega A has to be, this omega thing has to be cyclic.
Yes.
So that requires another constraint. That puts another condition. So maintaining that, we have this omega A and omega B.
So what I could not understand is why second one doesn't have omega prime and omega B prime.
Okay. This instantaneous, again the same. There is instantaneous jump. So the particle
remains the same.
The particle didn't realize that.
I see.
Right? It will change along the cold isothermal.
But the implication also is that no work is done along the peak jump. Right? Is that correct?
No, that is delta U is there. We calculated last time delta U is there because
omega is same, but lambda is different.
Lambda is different. That is why you get this K. So the change was like from K by 2 to K by 4. Correct? If I remember correctly. And then you have to average over with same omega A, the distribution, but that K by 2 to K by 4 difference will come. And that will give you the energy cost or the work in the adiabatic steps.
I didn't get it, but I will ask now.
So only the potential energy changes in the case.
Because this is the X and V doesn't change. It's so instantaneous.
Distribution remains unchanged. But
The state of the system remains same, but the operator changes.
K
Like
has
the K has changed. So now I guess it is pretty straightforward to get the, so from there with this one and 1 and 2, we will get lambda optimum. So what is my lambda optimized protocol? That from 1 and 2, and then this expression will get. So I am not writing it, it's like
Expressions for lambda in the two bands.
They are connected by jumps.
So
the jump length, so you can put the tau as in the boundary condition problem. So you put this tau hi here, okay, and let me just
and that will give you WB.
wait.
They are the same.
Wait, there is a how to compute the terms. Right, they are the same because omega you don't find, but when you calculate lambda, from there when you put the jump things, so they will be function of this, right? This lambda is this. You have to take the derivative and put it here, and then omega corresponding. So you will get lambda hi, lambda ci, right? There, when you put tau is this t is equal to tau hi, in one expression, and the other expression, same, P is equal to tau hi, you will get the jump after first isothermal. They don't match.
Yes.
Because of the omega dot. Correct? And then again you go to the next.
So you need a jump in
Lambda, yes. Because if there is a jump, there is the distribution will be different. This thing goes to no, there is a jump in lambda.
Matching, but it's just the jump.
It's just a jump in lambda, not in omega.
So ideally, we should get a determination and from there.
Yes.
And one thing, is hot isothermal and cold isothermal, don't they have different temperatures?
That will come now. This in this omega A. This will come.
There is additivity.
Yeah. So there is. So rest. So the rest. Once I am there in lambda, the rest. Do you know that like this? It follows. You can get. I'm not writing it. It's a big very long. But essential thing is this regarding optimization. Then you will find optimized lambda, optimized W, optimized heat, finally optimized efficiency. So they are all like big equations, but it is very, very straightforward. This is the only subtle thing that I want to tell you. Is the rest, okay, rest, let me ask the students, is the rest procedure clear for everyone?
So you find lambda Ci and lambda Hi.
Yes.
And then you take it, you find that lambda is equal to
What are the jumps?
You can find the jump. What is lambda optimization? Small this.
So when you put this lambda Hi and lambda Ci, you will get lambda optimum, right? These are the very particular functions. They are not any functions. Then that functions will optimize omega. That means it optimizes lambda because omega is related to lambda. So thereby we get optimized lambda, which I wanted.
So the optimized lambda has two values corresponding to Hi.
Two different functional form corresponding to Hi, corresponding to yes. And then there is a jump.
In the other two branches, their lambda changes from.
That you can find. That you can find here. Like you will. That's what you are asking. That you just put omega here. Different omegas will give you different lambda. You just put the right time there.
But you know the top and the the two lambdas at the extreme points, but in between the function, how it
function. So there is discontinuous. There is no continuous function. This is just jump. Like any, say you have this. And then this.
You were saying lambda. There is no function of lambda.
No, this is jump.
It is just okay.
Just you have to calculate jump, and that you need to calculate the internal energy. And internal this energy is what? So this is how we calculate additivity. What?
Omega into delta lambda.
Omega into delta lambda. That's it.
So finally,
Half. With a half. Half x square average. Omega into delta lambda half.
Those two branches don't contribute to.
They contribute. They contribute. They contribute to work. They contribute to heat as well. So the heat contribution coming from the cold isothermal to hot isothermal jump. So here I will stop. Oh, okay. Sorry. Yes.
so efficiency finally will be function of, all these things will come, but
So finally it will be okay. Efficiency it will be a function of temperature, but it will be okay. The once you find the efficiency, will find the in the